Hi, my name is Brian Hussey, and today's date is August 29th, 2025. So today I will be presenting my work on the combined spectral problem, and I did problem I, or number 9. So just to talk about what we're going to be talking about today, first we're going to dive into degrees of uncertainty and hydrogen deficiency index calculations. We're then going to look at the IR spectroscopy, followed by the carbon-13 NMR spectroscopy, and then proton NMR. And then we'll build the molecule that we figured out what our spectra was, and then I'll show you an overview of the tables that I filled out. So we were given that the molecular formula of the molecule is C10H12O. Now, to calculate degrees of unsaturation, we use the formula carbon minus, or the number of carbons minus the number of hydrogens over 2 plus the number of nitrogens over 2 plus 1. And doing this, we get 10 minus 12 over 2 plus 0 plus 1, giving us 5 degrees of unsaturation. So immediately we see that, and we're going to know that we're looking for an aromatic feature, potentially a benzene ring. Just to show you another calculation, the index of hydrogen deficiency, we know that the formula is 1/2 times 2 times the number of carbons, plus 2 plus n minus the number of hydrogens minus the number of halogens. This would give us the same 5 as our index of hydrogen deficiency. So moving forward, we're going to look at the IR spectroscopy, and we can see right around, just looking at the right-hand side of the spectra, we can see that around 2950 wave number, we see that there's an alkyl CH sp3 group. So that we can also look at the guide over on the left to help kind of figure out what some of these transmittances may be. But yeah, so we have the alkyl CH, or the alkyl sp3 CH group. Additionally, we see around 2700 to 2850 centimeters a Fermi doublet, indicating that it might be an aldehyde here, but we're not 100% certain. However, we do have a carbonyl, a transmittance around 1700 centimeters, which is normally indicative of a carbonyl, C double bonded to an O. So maybe with both of these, we might see that there is a potential for an aldehyde. Additionally, we have around 1600 an alkene C double bonded to a C. So this might be aromatic, given that there is also transmittance around 1550, which is in the aromatic range. So this is just talking about more of what I just spoke on. We have a strong C double bonded to O around 1700. Looks like an aldehyde, especially due to the next feature, which was that Fermi doublet, the C to H, around 2700 to 2850 centimeters. Together, these two features are diagnostic of an aldehyde. Additionally, we had the C double bond to C, which, and like I said earlier, due to the high index of hydrogen deficiency, we know that we're kind of looking for an aromatic feature, so those alkenes may be indicative that we do have a benzene ring present in our final structure. And then lastly, we had the alkyl sp3 carbon to hydrogen around 2950. And this is likely to be some sort of alkyl substituent attached to the benzene ring. So some takeaways after looking at the IR spectrum. It's likely that we have some sort of aromatic aldehyde attached to an alkyl group. However, we need to investigate a little bit further for a better understanding. So now moving on to the carbon-13 NMR. Again, I have the guide over to the left to help you figure out some of the values with the chemical shifts and what structures those may relate to. This time I'm going to show you the guide on the right, and then, or what I figured out on the right, and then talk about it more in depth. So around 190 parts per million, there was a strong polarization and pi anisotropy shielding, bringing this peak very downfield. So kind of going back, we see that this is indicative of the aldehyde. I actually am going to talk about this first. This is the aldehyde here around 190 parts per million. We also see that in the range of 120 to 160 parts per million, this is our aromatic range, and we see that there are a couple of different peaks here, which I will talk about. So the one signal around 155 parts per million represents the ipso carbon bonded to the aldehyde. This C is extra deshielded by the aldehyde, which is electron withdrawing, which makes sense because oxygen is a much more electronegative atom than carbon or hydrogen. In the 135 parts per million signal, this represents the ipso carbon bonded to the alkyl group, so on the other side of the benzene ring. This carbon is a little more upfield because an alkyl group is electron donating and not electron withdrawing. Then lastly, going back, we'll talk about these 4 aromatic carbons, or the aromatic C to H carbon bonds. And these suggest that this is a para-distributed benzene ring, meaning that both the aldehyde group and the alkyl group are on completely opposite sides of the ring, not in an ortho or meta positioning, in relative positioning to each other. And then lastly, we had 2 other signals a little more upfield here. We had a CH, which was pulled downfield by the benzene ring, and then 2 CH3 groups. So we know that the benzylic C to H bond, this is bonded to the alkyl, this CH is bonded to the ipso carbon of the benzene ring, and it's shifted slightly downfield due to ring current anisotropy. So this is the non-aromatic carbon of the CH bond experiences a little bit of an increased deshielding as kind of due to the ability of the double bonds to move around the benzene ring. Oopsies. And at 25 parts per million, we have the one signal of the 2 methyl carbons. So now for some takeaways. We know we now have a pretty good understanding of what molecule we may have. We know that we have an aldehyde, a para-distributed benzene ring with a benzylic CH group, and 2 methyl groups. So now moving into HNMR spectroscopy. Same thing, I have the guide over of the NMR shift values, the chemical shift values to the left, and then my findings on the right. So we see that we had a couple different peaks here. We had the 1H singlet on the left around 10 parts per million, and that's pretty indicative of the aldehyde. So we had the aldehyde H driven downfield by the carbon double bond to the oxygen anisotropy. And looking at the N+1 rule, because it was a singlet, N+1 equals 1, so N equals 0. So there's no neighboring protons on this aldehyde, meaning that the aldehyde is completely isolated from any other neighboring hydrogens. Oops. Then looking at these 2 doublets here, we see one a little more downfield than the other, and this one, as we kind of spoke about with the carbon, similar. It is a little more downfield because it's positioned ortho to, these hydrogens are positioned ortho to that aldehyde, so that's kind of going to swing them a little bit more downfield there, and then the other 2 are ortho to the alkyl group, kind of bringing them a little bit more upfield. So yeah, the 2 H's ortho to aldehyde are driven further downfield due to electron withdrawing capabilities of the aldehyde, and the other 2 are ortho to the alkyl group, further upfield due to positioning further from the aldehyde. Thus, these hydrogens are going to less feel the electron withdrawing effects of the aldehyde. And then looking at the N+1 rule with those, both sets of these hydrogens are ortho-coupled to 1 equivalent neighbor, because these are both doublets. So N+1 equals 2, so N equals 1, so they have 1 equivalent hydrogen neighbor. Then looking at this little septet down here around 3 parts per million, we see that looking at the N+1 rule, we have 6 neighboring protons on the 2 CH3 groups. So we know that these 2 CH3 groups are equal and are placed next to this the hydrogen of the septet. So that is going to be a CH group bonded to 2 CH3 groups. And then lastly, looking at the 6 hydrogen doublet placed here around 1.2 to 1.3 parts per million. Looking at the N+1 rule, it's a doublet, so N equals 1, or N+1 equals 2, N equals 1 neighboring proton. And since both methyl groups are equivalent, their integrations add to 6 hydrogens. So looking at this holistically, we have a very, very clear understanding of what molecule we may have. We understand the positioning of the hydrogens on the benzene ring. We understand where our benzylic methine group is positioned and what we are working with an isopropyl, and that we are working with an isopropyl group. So after assembling, this is what I came to for isopropyl benzaldehyde. So we see that on the left we have our aldehyde group attached in a para relation to our isopropyl group. So on both, these functional groups are on both sides of the ring, opposite sides of the ring. And then we have our benzene ring in the middle. So now just to look at our Spectra table, this is what I filled out. We talked about all this earlier, but just the filled out tables. This is the carbon-13 NMR Spectra table filled out, and the HNMR spectra filled out. Thank you so much.